Hi, in this video we are going to talk about binary search tree. Before we introduce binary search tree, let us consider this problem. We have a set of items and we want to perform these operations on the items. We want to search an item, we want to insert an item into the set, we want to delete an item from the set, we want to find out closest value in this set. What do we mean by closest? Suppose this set contains integers like 5, 10, 30, 50, and if your input is 29, then the closest value is 30. Even if 29 is not present, we want to find out what is the closest value that is present. If your set contains strings, then you want to find out closest value alphabetically. The last operation we have is sorted traversal. We want to print all items of the set in sorted order. Let us explore all the common data structures that we have studied so far and try to compare time complexities for these operations. Let's first consider unsorted array. Say we store all the items of our input set in an unsorted array. Now what will be the time complexity of inserting an item? It will be big O of 1. What will be the time complexity of searching an item? Since it is unsorted, you will have to traverse through the whole array and your search will be big O of n. What will be the time complexity of deleting an item? Say you want to delete 12, then you will have to move these items one position before. So deletion is also big O of n. What will be the time complexity to find the closest value? You need to traverse the whole array to find the closest value. So this is also big O of n. What is the time complexity for sorted traversal? You need to sort the array to get the items in sorted order. So that's going to be big O of n log n. Let us now talk about second option, which is sorted array. With sorted array, your search becomes faster. You can search an item in big O of log n time. But what about other operations? Your insert becomes big O of n. Because now, for example, in this array, I want to insert 5. I'll have to move everything one position ahead and then I have to create a place here for 5 and then I'll insert 5. So insert is big O of n now. Delete is big O of n, obviously, because of the same reasons. If I want to delete 12, I'll have to move everything one position back. Finding closest is also faster now because we can use binary search for finding the closest value. Sorted traversal is big O of n because your array is sorted. You simply need to traverse through the array and print the items or iterate through the items. That's big O of n now. Let us now talk about our next option, which is linked list. We store all the items of set in a linked list. Now, what is the time complexity for searching? We'll have to traverse through all the nodes of the linked list and it's going to be big O of n. What about insert? Insert can be done in big O of 1. We can insert an item at the head of linked list in big O of 1 time. Also, we can maintain a tail pointer and insert at the end in big O of 1 time. We can do insert both ways in big O of 1 time. Now, what about deletion? Deletion is again big O of n because we'll have to traverse through the list and find the item and then we'll have to remove it. Closest value is also big O of n. Sorted traversal, if your linked list is maintained in sorted order, then sorted traversal is big O of n. Otherwise, it's going to be big O of n log n. Please note that if you're using sorted linked list, then your time complexity for insert item is going to become big O of n. Because to insert an item, you will have to find the place where you will have to insert. For example, if you want to insert 17 here, you will have to traverse from here, then you will come here, then you will come here, and this is where you find the place for 17 and insert it. So insert becomes costly in linked list if you're talking about sorted. Other operations are anyways big O of n, so they are going to be same. So with sorted linked list, we get big O of n, sorted traversal, but our insert becomes costly now. We have talked about all the previous data structures that we have studied so far, and we have seen that many of the operations in these data structures are linear time complexity. Binary search tree provides search, insert, delete all operations in logarithmic time. We have search, insert, delete all in logarithmic. Not only this, finding closest is also logarithmic. And sorted traversal of items is linear. So this is the advantage of binary search tree. If you have these items or a subset of these items, then you can use binary search tree in place of these old data structures. Now, one more interesting thing. There is one more data structure that has time complexities of search, insert, delete as constant on average. This data structure is hash table. We have talked about it. This data structure is the best when you have insert, search, and delete operations or subset of these operations. And it beats binary search tree. But binary search tree can be helpful when you have these three operations and probably you have one of these two operations also. You want to find out closest or you want to traverse the items in sorted order. Not only closest, there can be other operations which can be logarithmic in binary search tree, like finding the floor of an item, finding the ceiling of an item, finding greater, finding smaller. These all operations are basically around closest element. So when you have closest operation or operations around closest, you can use binary search tree. Please remember one thing, binary search tree in itself does not have this logarithmic time complexity. We get this logarithmic time complexity when our binary search tree is balanced. In general, binary search tree time complexity is big O of h, which is height of the binary search tree, and height can go linear. But in case of balanced, it's log n, and we can make sure that binary search tree remains balanced. We'll be talking about this balanced binary search tree in the upcoming videos. In this video, we have mainly talked about different operations, their time complexities, and we have talked about the applications where binary search tree, in particular balanced binary search tree, fits in. In the next video, we'll introduce binary search tree, we'll introduce its structure, then in the upcoming videos, we'll discuss these operations in detail.